Media Tea Time Talks, a channel created by young porous media researchers for young porous media researchers that aims to share and interact with the broader scientific community. I am Nara Brandão from Federal University of Uberlândia in Brazil, and I will be your host today. In the studio with me, we have Javier Santos at the University of from the University of Texas at Austin, and Kamal from Eriot University, and Marcel Moura from University of Oslo. Today is a very special session, as this is the first and official one that our channel has been invited to join the InterPore Young Academy. So, to celebrate it, we are going to have an InterPore Norway edition. We are happy to have Hal and Santanu with us. Please feel free to type your questions in the chat. We are going to have 5 minutes for questions and answers. I also invite you to subscribe to our channel to be notified about the next talks. So, let's start. Hal is our first speaker. He is a PhD student from the University of Bergen in the mathematics department. He works on numerical modeling of fractal deformation and propagation in pore elastic media. Hal, thanks for being here, and please, the floor is yours.
Yeah, thank you very much for the kind introduction. So today I'm going to talk about the numerical modeling of fracture deformation and propagation in porous media, poroanalytics media. The motivation of this work is from the geothermal reservoir system. A geothermal reservoir is a vulnerable hot rock in the subsurface, which can exploit in terms of heat. The heat producing from the surface is necessary to present a transport fluid like water. So, the principle is to drill a couple of wells in the enough deep to reach the optimum operation temperature. Then inject water from one well. We can employ hot water from another one. Water can flow from well to well because two reasons. Rock is a permeable porous media, and there are many fractures existing in the rock. The water injection sometimes causes seismic events because thermal, hydronic, chemical and mechanical interact with each other. However, identification causality is not possible because it of course deep underground. So it is necessary to develop a mathematical model to predict the interaction between thermal, hydronic, chemical, and mechanical during the injection. As you can see here, the structure of rock in the subsurface is so complex. It includes many existing fractures at different sizes. In my study, I'm modeling the structure by using degree fracture matrix model. This model can represent explicit both matrix and fracture, so it allows for accurate modeling of interaction between them. A full modeling of this problem is very complicated because we not only investigate the behavior of structure and processes, but also investigate the interaction between them. My research is focusing on the interaction between fluid injection and mechanical behavior in rock, like deformation, contact mechanics, and fracture propagation. The matrix is model based on the bioporoanalticity model, and I consider the effects of fluid flow, friction, contact, and fracture propagation. To do that, I will present a mathematical model followed by numerical strategy. I will present some numerical results to solve the probabilities of my model. The mathematical model is developed based on some assumptions. For the matrix, the relationship between strain and deformation is based on small deformation theory. Stress causes not only In this subsumption, stress caused not only by strain but also by fluid pressures. Even rock in the porous medium, I model it at the isotropic, homogeneous, and linear anestheticity based on equivalent model, in which property of rock are represented by Young modulus, Poisson ratio, porosity, and permeability. For flow, I'm considering incompressible, steady, and constant viscosity flow. Flow in the fracture is reduced dimension at nominal flow in infinite parallel place with no slip condition on the wall. For the fracture contact mechanics, I'm, co- I'm considering the friction between fracture face by Columbus friction model. Fracture is allowed for dilation but not allowed for penetration. And for fracture propagation, I'm considering the mid-pole fracture model. This model allows for fracture propagate whichever direction they can go, and the correct emerges if the tangential stress achieved with the criteria value. So with the assumptions, the mathematical model for matrix is represented here, with the conservation of momentum, conservation of mass, and Darcy flow. Oh, a bit late. And the mathematical model for flow inside the fracture is represented here. Sorry, I cannot control my presentation.
Oh, can we help you? Like, what's happening at the moment?
Okay, now I can control it. I cannot control it.
Okay.
Okay, now it's okay. And
Okay.
yeah, sorry. For flow, the mathematical flow inside the fracture is represented here. We can see the effect of the fluid flow from the fracture into the matrix here. And the permeability in the fracture is defined by the cubic law. And I assume the flow is the isotropic flow. So that means the tangential permeability and normal permeability is equal. And for the fracture contact mechanics, the Colombo friction, non-penetration condition, and dilation is present here. So I will not go to detail for this because it's a bit complicated to explain here. So the mathematical model for kernel and propagation is represented in this slide. The fracture emerges if stress aggravated with material toughness criteria. Then the direction of new fractures can be determined through the stress intensity factor, and the length of the propagation is determined through the energy achieved. In my research, the stress intensity factor are determined by quarter point element. The summary of the mathematical model for coupling fluid flow and fracture propagation in porous medium is shown here. So as you can see, this model is very complicated, impossible to find exact solution. So using numerical method is the best choice. Before decide to use what numerical method to solve about questions, I must remind you the characteristic of crack in the rock. So you can see a light in some figures here. The size of a block of rock can be up to kilometers, but the length of existing fracture is only a few millimeters to meter. And the aperture is very small compared with the length of fracture. So I plan to use a multi-scale simulation for this problem. For the simulation domain called macro scale, I use a cost method to save the computational cost, and I consider the interaction between flow and deformation of matrix and fracture. Then, at its tip, I consider a small box called micro scale. I use a finer mesh that captures better thread around the tip, and I evaluate fracture propagation in this scale. And then I update again in the macro scale. To do it, I combine my study with open source developing by my group named Profile. At each time step, I using Profile for solving poroelastic deformation of existing fractures at the macro scale. Then, I'm using micro mechanical solution at boundary conditions in micro scale to determine a new fracture. If any fracture is propagated, I have to update geometry before I go to next time step at macro scale. The detail of the simulation is shown in this flowchart. It is a bit complicated to explain detail here, so I will keep this. But if you have if you interesting about it, you can contact me. So in numerical section, I will present two examples to show the accuracy of and robustness of my present model. The first is doing for microscale validation purpose. I consider a compression rock disk with an existing fracture, and for the second one, I consider a porous media domain with geometry and boundary condition shown here. Remember that to determine if a fracture emerges, we have to compute the stress intensity factor first, K1 and K2. So, for this example, we can see how good my method is at estimating the stress at the corrective. So did they compare with analytical solution, experiment data, and with the red dot in my results. So a good agreement with both the analytical solution and the experimental data is shown here. For the propagation comparison, as you can see, result from my model is good agreement with experiment data. Fracture is propagates in the symmetric way and is linearity. So now for a super complicated case in which I consider the interaction of injection, shear slip, flow, deformation, and propagation. I use the geometry model and material parameter also here. I do the simulation in 90 minutes, in which quarter is inject to pre-existing fracture from 10 to 40 minutes. So here are the result I got. So before the injection, the stress at fracture tip is almost constant because of momentum and mass conservation. When injection starting, the normal traction, the green one here, the normal contact traction suddenly drop. It must fracture slip. At K2, the rest one like increasing, and fracture is start propagate from here. At the first propagation, fracture propagates quite fast because the accumulation of energy. After that, the energy is reduced, so we need to constantly inject a Y to make the fracture propagate again. When we stop the injection from here, pre-existing fracture is close and contact normal traction is increasing quickly and the fracture is stopped propagates. The deployment and pore pressure fields after 90 minutes are shown here. So you can see the pre-existing fracture is contact and sleep at this time. So, uh, so you can see in this talk I have present a multi-scale simulation for fracture propagation in porous media. I do the simulation of flow and deformation of fracture poroelastic media using control volume method in macro scale. And I do the quasi-static simulation of fracture propagation using the finite element method in micro scale. And the interaction by Bruce is just much for attention and feel free if you have any questions.
Thank you very much for your presentation, Hao. It was very nice. It's a very interesting topic. If anyone from the audience has any questions, I'll pass along the speaker. But first, I have a question of my own. I know coupling all the numerical systems can be quite challenging, right? And you probably have spent a good amount of time dealing with that. What was the main challenge into coupling the three models that you're presenting here?
Yeah, thank you very much for the question. So we have a lot of challenging. So first, the first is how to simulate the flow in the fracture. It is very difficult. So I have to use the reduced dimensional model to modeling it. The second one is how we can define the new fracture, because you know the scale of domain and fracture is very different. We have the very big domain, but we have very small fracture. How we can define the new fracture, because sometimes fracture is not propagated like high enough to define in the macro model, macro scale. So we have to define when we add the new fracture in the macro scale. And also difficulty coding, because here I combine finite element method and finite volume method. For the finite volume method, I simulate in the macro scale, and in the micro scale, I use the finite element method. So how to combine finite volume and finite element together is also on the challenging. The next one is how we can find the real data to run the model, because now the data I designed by myself, but I'm not sure it's correct. So how we can find the real data? How we can find the amount of inversion, the principal stress in the rock, the stress in this sector? So we have many data, like 20 data we have to determine, and how we can find it. Yeah.
Thank you very much. If anybody else has questions and you're watching this later, feel free to email our speaker and he'll kindly answer whatever questions you might have. Thank you very much, Hao. Now we're moving on with our next speaker. Our next presenter is Santanu Sinha. He is a researcher at Pore Lab in Trondheim. In there, he's investigating flow through fractures using pore network models. Today, we have a very interesting talk lined up. He will be talking about disorder porous media and nonlinearity in two-phase flow. So without further ado, Santanu, please take it away.
Yes, can you hear me? Hello, yeah. Okay, so thanks for giving me opportunity Okay, I have to look in this side. So thanks for giving me opportunity to present our work here. I'll be talking about the nonlinearity that we see in the two-phase flow in steady state, and how different disorder in different system parameters control this nonlinearity. And my collaborators here are Subhadeep Roy, who is a postdoc, Hursanai, Haijong, Hakon, they are the PhD students. Martin Breivik, who is a master student, and Professor Eve May and Professor Alex Hansen. So starting from the very basics, if we have a single fluid, then we have this Darcy law. The Q is linearly dependent on the pressure drop. And if we have two fluids, then we can also have, in a simple system, we can still have a linear relationship between the flow rate Q and the pressure drop with additional capillary pressure term. But as soon as the system gets a little bit complicated, for example, this type of tube with a varying radius or porous medium, then the relation between the flow rate and the pressure drop in the steady state no longer becomes linear anymore. And that's how this nonlinearity comes from. And here, first of all, I'm talking about the Newtonian fluids here. So viscosity does not depend on the shear stress at low Reynolds number, and also non-deformable porous media. That means that the pore space doesn't change with increasing pressure drop or something like that. So this nonlinearity, it all started long back, around 2009, from the lab of Professor Knut Molle in University of Oslo. They are studying the injection of water, glycerol mixture and air through the helicocell filled with glass beads, and they found this: the delta P in the steady state and the pressure drop varies with the capillary number with this relationship exponent. And this translates to this relationship: the Q, the flow rate, goes with delta P to the power exponent 1.85, which is more than 1. And they also had an analytical argument, and they said that the Q should be proportional to the quadratically dependent on the pressure drop. So we looked into it long back, and we had this mean field calculations for a homogeneous porous medium, and found that this flow rate varies with the pressure drop with this quadratic relationship, where this PT, it's a global threshold pressure below which there is no flow. And there is also a crossover to a linear regime when capillary forces becomes insignificant. And then we did numerical work with the dynamic pore network modeling, both in 2-dimension and 3-dimension with reconstructed porous medium. Now, this pore network model I am not going to describe here today. If you are interested, you can have this recent article where we have all the technicalities about this model to how to implement it. So with this pore network model, we had this agreement with this result. So at low flow rate, we have this quadratic relationship, and at there is a crossover to linear relationship both in 2D and 3D. And this 3D work was in collaboration with experimentalists, and they also found the same behavior with the 3-dimensional porous medium. So beta equals to 2 at low flow rate, and beta equals to 1 at high flow rate. And this thing was easy to understand in a simple way. If you have a network with links who has thresholds distributed over a regime, and as we increase the pressure drop, more and more links are active or becomes open. So the increase in flow rate will be the conductivity multiplied by the increase in the pressure drop, and this conductivity itself is a function of the pressure drop because of this more and more links opening. And so the pressure drop, this Q becomes this way becomes quadratic because there is two dependence on the pressure drop here. And when there is all the links are open, as this K becomes constant, and we get back to this linear relationship. So this was okay to understand how it works in a simple way. And then there was more studies came up in last 1 decade. So this was a Lattice-Boltzmann study. They found beta equals to 1 in this nonlinear regime. This was in 2015, an experimental study. They found beta equals to 1.54, which is for a specific type of porous medium. This is a more recent result, 2020 sandstone sample, beta equals to 1.67. Even more new result, beta equals to from 1.35 to 2.27, and that depends on the fractional flow. So all these studies found that beta is, the relation is nonlinear, and there's a beta, but it varies depending on many things. So we started looking onto this from a very bottom-up approach. We started with a single tube with this varying diameter. You can think about a lot of pore throats in between pore bodies. And for a sinusoidal type shape of this pore, we can calculate this time averaged expression for the flow rate analytically. And we have this square root dependence with pressure drop and flow rate. And here this gamma is a global threshold pressure for this link, which is a function of bubble sizes, pore radii, and also the wetting angles. So then we go to the bundle of such tubes with the distribution of this gamma. And so all these tubes have different gamma, but they have everything else is same. And then by integration, we can calculate the total flow rate to this bundle. And we get beta equals 2 for uniform distribution when there is a no lower cutoff in this distribution. And if we put a lower cutoff in this distribution in a certain range, we get beta equals 3/2, this is 1.5. And these are analytical results. And also we can go for a power law type distribution. And we have beta equals to alpha plus 1, where alpha is the exponent related to this power law. And if we put alpha equals to 1 here, we get back into this uniform distribution result. And it's a lower cutoff without a lower cutoff. And if we put a lower cutoff here in this power law distribution, then we cannot do numerical analytical calculation. We have numerical calculation, and we get beta equals to alpha plus 2. Here also, if we put alpha equals to 1, we get back this 3/2. Now this gamma here, this distribution is not a given quantity. It depends on many things. So if we look into this expression for gamma, we have this. So this theta is the wetting angle. This is a given quantity for the porous media, can be. So if we take a distribution of the wetting angle, for example, we can calculate Q, and this translates the problem to a mixed wet porous media. We can also take a distribution of the R, pore radii, and we can find the total flow rate here by integration. And also remember that this R also appears in the expression for Q here also. So these two integrations, theta and R, with different dependency on R and theta. So we studied these two problems individually. The distribution of these are in the pore radii. Here, first we started the capillary bundle model, where we get both for uniform distribution and for power law distribution this 3/2 exponent. And remember that here we have a cutoff both in lower side and the higher side. And then this capillary bundle tubes are disconnected. So we moved into the pore network model, and we took a large number of distributions, two types of distribution with the uniform and this power law type distributions with a large number of distribution parameters. This is the power law related to the distribution, which determines this shape, and this is the width of this distribution. And we have this full picture. So this is in the x-axis we have beta. This is the exponent related to this nonlinearity, and this is PT. This is the crossover pressure where system goes from nonlinear to linear. And this axis shows the variation in the saturation. So in this direction we are going towards more single phase flow, and you see beta is going towards 1 here, linear relationship. This axis varies the shape, this alpha. So it starts here, it is the uniform distribution, alpha equals to 0, and here is beta equals to 2, and it goes here towards 1.5 continuously. And this is the width of the distribution, and that determines how many links, when all the links are open, things like that. And that's why this changes this crossover pressure in this direction. So we had this full picture from this pore network model, depending on the different parameters of the distribution here. And then we studied the distribution in the wetting angle with the capillary bundle model. For uniform distribution, we have these two numbers, 1.5 and 2 for this nonlinear regime, and then it translates to the uniform to the linear regime for uniform distribution. And we also had this normal distribution, because that's the distribution people generally observe in the experiments. And here we have 2 beta equals 2 for the quadratic regime, nonlinear regime, and then 1 here, but there is also a crossover regime with a very high beta, and this shows when the links are opening in a much faster rate compared to this previous regime. And this shows how the distribution can control this shape of the dependency. And then we also had the pore network model, where also we have the values of the beta as a function of the mean of the distribution of this wetting angle, and also the width of the distribution of wetting angle. And this also very much explanatory results. For example, this one for mean when 90 degrees. So we have the normal neutral weighting angle. So there is no capillary force. So beta goes towards 1. And away from that, beta is increasing towards 1.8 or 2. And here also we see the similar behavior and show the full picture. And the last thing I want to say that is something is a transient, as a drainage. It's not a steady state anymore. So we are injecting the non-weighting and less viscous fluid in a high viscous fluid. And there you can see this kind of fingers. Now, if we take the average of this finger with the frame of reference that is fixed at the tip of the finger. So as the finger is moving, we have this frame of reference is also moving. And if we are average over many time steps and also many realizations, we get this grayscale. And this shows the shape of the fingers. And this shape doesn't change with time because the frame is moving. And then we can calculate this growth of the finger as a function of the distance from the fingertip. And we measure, if we measure the pressure drops also, we can find this relationship between the growth and the pressure drop for a given distribution of the thresholds. And for a uniform distribution, we have again this quadratic relationship between the pressure drop and growth. And this growth is directly connected to the flow rate, because if we sum over all the growth for a particular unit time, you get back this flow rate here. So it's a very similar picture here. And this is the numerical results where you see this nonlinear dependency between the pressure drop and the growth. And here, but here this relationship shows this exponent looks like much higher than 2. That means that this distribution may not be linear. But this is a very preliminary result. We have only few data points close to the fingertip, so we need much larger system with better numerical results. And so this all bring to the conclusion. So I studied this steady state two-phase flow, the nonlinearity as a function of disorder in the pore radii and a disorder in the weighting angles. And with the two models, one is capillary bundle model, where we see that the beta mostly either 1.5 or 2. And the links doesn't talk to each other here, the disconnected links. And when we have a pore network, when the links interact with each other, we get a continuous variation from 1.5 to 2. And that brings to the question that what is the role of network connectivity here? Because if you give a same distribution of the pores, more connectivity in the links will give more flow rate. And also, if can we do the experiments? For example, if we have a 3D printed porous media where we can generate a certain number of distributions specifically, and we can study the flow here, and can we verify the results, numerical and analytical results. And then we studied the viscous fingering, where we see this growth varies non-linearly with this pressure drop. And here also it looks like that the origin of this non-linearity coming from, again, from the disorder. So here comes the next question, that whether this exponent beta in the steady state has any relationship connection with this alpha. So yeah, so that's all for today. Thank you very much.
Thank you, Santanu, for this really great talk, and I really enjoyed it. And also, it's good to see that you set up the introduction part very nicely, very basically to teach people that what you're really looking at. But actually, one question I had is, but okay, before I ask, I would like to ask people, if they have question, please type in on the right hand side of your window. I had a couple of questions, but I think you already answered in the last slide. Because my one question would have been that if you have validated your results, and it looks like you would be, or somebody else in the group would be doing some experiments to validate these things. Because these are interesting features, because you see different between capillary bundle and pore network model. And also with pore network model, you can't capture the physics, fully physics, but they are easy to use, and you can do lots of sensitivity analysis on that. Well, just okay. The second question would be like, what's the domain size? Maybe I missed that part.
Sorry, the question: what is the what size? The system size?
Domain size you use for.
Oh, so the links, the networks, we have around 64 by 64 links, and sometimes 128 and 128 links, like that. So the links are 1 millimeter of length, and they have generally like 0.4 millimeters to 0.1 millimeter in the radii, and the disorder is there. And also for the reconstructed porous medium in the 3D, we have around 3000 kind of pores.
Okay. Okay.
Yeah.
And do you see any difference? But I'm not really sure if you change the domain size, any effect? Maybe in a very mean way, if I ask if you have any REV effects on this.
Yes.
Beta.
So one that is in archive from long time. We had to work on that. That is that if we keep on increasing the system size more and more, larger system size, the crossover regime where it goes from nonlinear to linear, this crossover point goes to more lower and lower. So it looks like that this linear regime is increases with increasing the system size. And that article is in the archive, but we need to do a little bit more calculation from the referee. So we are working on that. So there is a system size effect is there, where how this nonlinearity, for infinite system. But for the experiments and for the numerics for the lab kind of length scale, we always see this nonlinearity. Yeah.
And the last question before I ask the other people in the studio if they have any question, you mentioned because this factor already captures alpha, and then alpha captures the wettability. Did you run with the many different contact angles? Do you see difference, let's say, from water wetting system to especially intermediate wetting system? Do you see any big difference in your results?
A big difference in the sense that here we have, for example, this one. For example, we have these two plots basically. I mean, for now we have only looked into this nonlinearity, how this total flow rate varies with the total pressure drop in the steady state. So, and this is captured in these two plots, and here we see that, for example, here if we have theta equals to 90 degree, and there is the width of the distribution is 0, for example, that means that the contact angles, there is no capillary forces because it's a neutrally weight, and that gives this linear behavior, beta equals to 1. And if we go away from this, you get around 2. So we see this variation, a continuous variation in the varying the weightability. So that is there.
And if you keep increasing further, sorry, I said intermediate, but let's say if you keep increasing that, what do you expect?
Okay, so for we have the most of the results we have till these two limits, this 1.8 or 2. So we don't, so far we have not received any exponent which is more than 2. So always we see the higher limit is 2, the quadratic dependence, and then it generally decreases around 1.5, and in some cases close to 1 if it's going towards neutrally weight, something like that. So the standard regime in most of the cases, for example, this one, we see that it saturates around 1.5, doesn't go beyond less than 1.5, and that's the regime, that's the limit we see in the capillary bundle, 2 to 1.5. So that's something we see. And also if you see in the experimental results here, this one, here also you see that it's like 2 to 1.5, something in this range generally the people see. So I don't know. Yeah.
No, so it was my mistake to. My question wasn't clear. But what I meant, like, if you keep increasing the contact angle because you go to 90 degree, and if you keep increasing that, what would you expect?
Okay.
I'm sorry, my question wasn't clear.
No, that's okay. Yeah. So this is the regime we consider here is this. So then this 0 degree means is basically same as 180 degrees. So this either this way or this way. So so we have the whole range, and this is normal distribution. So this is the mean of the contact angle, but it tails towards kind of like this. Yeah. And for 0 degree with delta is 0, that means we have theta average is 90 degree here, so 0 degree is this one, so it goes towards the maximum value, which is kind of close to 2 or something like that. Yeah.
Okay. Well, thank you, Santanu, for
thanks for having me.
Yeah. So anybody in the studio has any question?
I have a quick one.
I can see Yeah, please go ahead.
Santanu, do you think are there any film flow effects in these models, or is it possible to incorporate any film flow effects? And do you expect that to change in any way the nonlinear behavior?
Yes, that's something we should do, but film flow is not included in this model. So this only considers the systems where we do not have film flow. So it will obviously, of course, it will change the results. So we do not have the results for film flow yet.
But is film flow something that can be incorporated into like pore networking model, or would it be like a completely different way to simulate the problem?
No, it was already incorporated in pore network model. So there was a PhD student, Glenn Thora, in our group a few years back, who incorporated the film flow with the same model. But for me, I have not gone into much, but because it makes this solution of this set of linear equations 10 times more complex, because you have now we have only resistance effect when you're solving the flow equations, and including film flow includes a capacitance kinds of effect between the flow equations when you solve them. So it makes it's very complicated. So I have not looked into that much. Yet.
All right, super. Thanks a lot.
Yeah.
No, I think it's a very nice question. Yeah, that is about thin film flow. Yeah.
Yeah,
Anybody
that's
have
something important. Very want to do it. Yeah.
Sure. Anybody else has any question, comments? Okay. If we don't have any question, we'd like to thank Santanu for this great talk.
Yeah,
and
thanks very much for having me.
It was a pleasure actually to host you. Thank you for accepting our invite, and thank you to both the speakers. In fact, yeah. Okay, so I think we'll move on. I think we'll finish this talk because now it's time to wrap up, and there's some announcements there that we'll take a pause for some time. It's a summer break, and people will enjoy going to the beach if possible, if the current conditions can allow. And we'll come back on the 17th of August with our new presentations. And as we've already advertised, we are under this InterPore Young Academy now, and this is gonna go much broader now in terms of audience, in terms of having more different topics. So please watch out for the space, and we'll keep you updated through our network with the LinkedIn and with the Twitter with the new talk and the new speakers. And we'll definitely bring special sessions, especially like the one now we did with Norway, and the previously we did with Brazilian special. So we'll bring these time to time, and hopefully you enjoy the summer break. And thank you everyone in the studio and joining us today. And we'll see you soon in August. Take care. Bye.